Hey everyone, I hope you're doing well today. In this video, I'm going to be talking about how to calculate average atomic mass. While the timestamps are here, they're also linked in the description so you can jump around to the parts of the video you need. Now you may be wondering why I drew some tacos. Besides the fact that I love tacos, I'm going to attempt to use them to help you understand isotopes better. Imagine we have 3 different tacos. This first taco is pretty standard and has some meat, some cheese, some sour cream, some salsa, and some lettuce. This middle taco has all the same types of toppings but also has guacamole added to it. And this taco on the right is similar, but there's hot sauce added onto it. While these tacos are a bit different from each other, at the end of the day, they're still tacos. While some versions of tacos are more abundant than others, the different types of tacos combined make up the category of tacos. Now let's look at something a little bit less tasty, like uranium. For the sake of this video, try to think of uranium as our tacos. While there's a general element uranium, there's actually some different types that make it up. These different types are called isotopes. We have uranium-238, uranium-235, and uranium-234. These 3 different versions of uranium are kind of like our 3 different types of tacos. While uranium-238 is the most abundant and the most common, we still have uranium-235 and 234. While most people in the world may eat the standard taco, there's also going to be some people that prefer to have guacamole or prefer to have hot sauce. Since everyone eats different types of tacos and different amounts of them, to find the average taco, we'd have to proportionally weight the most popular tacos over the least popular tacos. What I mean by that is, when we look at the 3 isotopes of uranium, we need to see which isotopes are more abundant than others. Factoring in the atomic mass units, or AMUs, and the natural abundance, we can calculate the average atomic mass of each element. Let's get into some practice problems and do some math together. Here in example 1, let's practice calculating average atomic mass. Notice how we have 2 isotopes of chlorine. We have chlorine-35 and chlorine-37. We're given their respective atomic masses, and we're also given their percent abundance. While there are 2 isotopes of chlorine, chlorine-35 has a higher percent abundance. To find the portion of the average atomic mass that chlorine-35 contributes, we need to multiply the atomic mass of chlorine-35 by its percent abundance. The atomic mass of chlorine-35 is 34.969 AMUs, and we're going to multiply that by the percent abundance in decimal form. To change the percent abundance to a decimal, we just divide it by 100 or slide the decimal 2 spots to the left as a shortcut. As a decimal, the percent abundance is going to be 0.7577. Multiplying these 2 together, we're going to get about 26.496 AMUs. Now let's calculate the portion of the average atomic mass that chlorine-37 contributes. The atomic mass of chlorine-37 is 36.966 AMUs, and we're going to multiply that by the percent abundance as a decimal. Dividing 24.23% by 100, or sliding the decimal twice to the left, we can write the percent abundance as 0.2423. Multiplying these together, we're going to get about 8.957 AMUs. Chlorine-35 contributes about 26.496 AMUs to the average atomic mass, and chlorine-37 contributes about 8.957 AMUs to the average atomic mass. Adding these 2 atomic masses together, we get an average atomic mass of chlorine of 35.453 AMUs. This is the average atomic mass of chlorine. Let's try a similar problem in example 2. Here we're given 2 isotopes of lithium, along with their percent abundances. Our 2 isotopes are lithium-6 and lithium-7. Here we have the atomic mass of each isotope. Looking at the percent abundance, we can see there's a lot more lithium-7 than lithium-6. Let's find the average atomic mass now. Let's start by finding what the isotope lithium-6 contributes to the average atomic mass. We'll start by taking the atomic mass of lithium-6, which is 6.01512 AMUs, and we're going to multiply that by its percent abundance as a decimal. Sliding the decimal over 2 times to the left, or dividing it by 100, the percent abundance can be expressed as 0.075. Multiplying these together, we're going to get 0.451 AMUs. Lithium-6 contributes about 0.451 AMUs to the average atomic mass of lithium. Now let's find how much of the average atomic mass comes from lithium-7. Its atomic mass is 7.01600 AMUs, and its percent abundance as a decimal, dividing it by 100, is going to be 0.925. Multiplying these together, we get about 6.490 AMUs. The isotope lithium-7 contributes about 6.490 AMUs to the average atomic mass. Hopefully this makes sense because there's a lot more lithium-7 than lithium-6. Adding these AMUs together, we're going to get an average atomic mass of about 6.941 AMUs. That's the average atomic mass of lithium. Now let's try calculating the average atomic mass when we're not given a table to organize our information. Titanium has 5 common isotopes: titanium-46, titanium-47, titanium-48, titanium-49, and titanium-50. It looks like we're given the percent abundances and we're looking for the average atomic mass of titanium. To find the average atomic mass of titanium, we need to find out what each of these isotopes contribute to the average atomic mass. For titanium-46, we're going to take its mass of 46 and multiply that by 8%. Converting 8% to a decimal, this is going to be 46 times 0.08, and that comes to 3.68 AMU. This is what titanium-46 contributes to the average atomic mass. For titanium-47, we're going to multiply 47 by 7.8%. Converting 7.8% to a decimal, this is going to be 47 times 0.078. This comes to about 3.666 AMUs. For titanium-48, we're going to take 48 and multiply that by 73.4%. Converting the percent to a decimal, we're going to multiply 48 by 0.734. This comes to about 35.232 AMU. For titanium-49, we're going to multiply 49 by 5.5%. Converting 5.5% to a decimal, this will be 49 times 0.055. This comes to about 2.695 AMU. And finally, for titanium-50, we're going to multiply 50 by its percent abundance of 5.3%. Converting 5.3% to a decimal, that's going to be 0.053. This will give us about 2.65 AMU. Adding these masses together, we find that titanium has an average atomic mass of about 47.923 AMU. In example 4, we're going to practice calculating atomic mass of an isotope given the average atomic mass. It looks like we're dealing with 2 isotopes of copper, copper-63 and copper-65. While we know the atomic mass of copper-63, we don't know the atomic mass of copper-65. Since we have the average atomic mass of copper, we can actually work backwards to find out the atomic mass of copper-65. Just like in the last few examples, adding the atomic mass units of copper-63 and copper-65 will get us our average atomic mass of copper. Since we're not looking for the total, we can set up an equation to work backwards. First, we'll take the atomic mass of copper-63, which is about 62.9298, and multiply its percent abundance as a decimal, which is about 0.6909. And we're going to add that to the atomic mass of copper-65, which we don't know. I'm going to call this X. And we're going to multiply that by its percent abundance as a decimal, which is about 0.3091. What makes this example different from the last few is the fact that we actually know the average atomic mass. We're given it in the problem, and it's 63.546 AMUs. Multiplying these two together, we're going to get 43.478. And multiplying these two together, we can write this as 0.3091x and set that equal to 63.546. At this point, we just have a 2-step equation. Our goal here is to get x alone so we can find out the atomic mass of copper-65. To start off, we'll subtract 43.478 from both sides. That way these cancel out, and we'll be left with 0.3091x is equal to 20.068. Dividing both sides by 0.3091, and this is about 64.924 AMUs. Therefore, we can say the isotope of copper-65 has an atomic mass of about 64.924 AMU. Example 5 is going to be the last problem in this video. It looks like magnesium has 3 naturally occurring isotopes. Just like the last example, we're given the average atomic mass. We're going to have to work backwards to find the atomic mass of magnesium-24. Here you can see I set up an equation where we take the atomic mass of each of the 3 isotopes, and the sum of it will be the average atomic mass. Since we don't know the atomic mass of magnesium-24, we're going to use x to represent it. Rewriting its percent abundance as a decimal, we'll write 0.7870. For magnesium-25, we're going to multiply its mass of 24.98584 and multiply that by its percent abundance of 0.1013 as a decimal. And for magnesium-26, we'll take its atomic mass of 25.98259 and multiply that by its percent abundance as a decimal of 0.117. The sum of all of this is going to be equal to the average atomic mass of 24.3050. We can write the product of x times 0.7870 as 0.7870x. Multiplying these two together, we get an atomic weight of about 2.5311. And multiplying these two together for magnesium-26, we get about 3.03996. This is equal to 24.3050, or the average atomic mass. Adding the two atomic masses that we know together, we get about 5.57106, and that's added on to the atomic mass of magnesium-24, which is 0.7870x. Adding these together, we're going to be getting 24.3050. Subtracting both sides by 5.57106, these will cancel out to make 0, and we can write 0.7870x is equal to 18.73394. Dividing both sides by 0.7870, these will cancel out to just make one x, or just x, and that's going to be equal to about 23.804 AMUs. Therefore, we can say the isotope of magnesium-24 has an atomic mass of about 23.804 AMU. And that wraps up this video on average atomic mass. If you found it helpful, please let me know in the comment section below or by giving the video a thumbs up. Keep up the good work, and good luck in everything that you're doing.